welcome. We are doing our last lecture. As they say, last but not least, we leave one of the best topics to the end, and probably the hardest topic, okay, cosmology. You could develop a whole course and teach a whole semester just on this topic. So this is an attempt, a feeble one at that, to try to take this big, giant topic and try to make it all in one day, you know. So I'm trying to give you the most crucial things about the topics in one day, but as I said, you could make a whole course out of this. So cosmology is a subfield of astronomy, okay? Remember the TV series Cosmos by Carl Sagan. So cosmos means universe, and that's where cosmology comes from. Cosmologists study the ultimate questions about the universe. These are questions that have been asked for generations of mankind before we ever lived, okay? When the caveman first wandered and looked in the sky, how did the universe begin, you know? So people have been cosmologists by nature forever, you know, as far as we know. How old is the universe? What is the shape of the universe? These are all questions that have always come into our minds, you know. What is the universe composed of? You know, are there stars, planets? Besides stars, planets, gases, what else is there out there? Of course, are there other civilizations there that are living in other planets? Those are good questions. How will the universe end? If it will end, will it end? Will a new one begin? Or is it, will this one end and nothing new begin? How big is the universe? You know, that's also a good question. Is it infinite? Is it infinite in time, and is it infinite in space, you know? And you could keep asking many, many more questions. How many universes are there? Okay. Are we the only universe? Are there other universes? Are there other life forms? I try to cover the majority of the questions, but you can keep coming up with questions like this forever. So what we're going to focus on is modern cosmology. Modern cosmology, I'm going to define as the beginning from Edwin Hubble's discovery, the Hubble law. Okay, so that's about 1920s. There was a big debate raging in the 1910, 1920s whether the Milky Way galaxy was the only galaxy or not. And there was a group of proponents that believed Milky Way was the only galaxy in the universe, you see. Then there are other people who said, no, there are other galaxies. And so what happened was Edwin Hubble did a lot of study about spectral type of stars and the Doppler shift that those stars were experiencing. And he used the telescope on Mount Wilson Observatory north of Pasadena. So Pasadena is famous for that. Mount Wilson Observatory became famous for that. So he did studies of spectral types using the Doppler shift, and we learned about Doppler shift before, where a galaxy, if it's coming towards us or going away from us, it's going to have a shift in its spectral lines. So he did a bunch of galaxies. He did their Doppler shifts and stuff. And what he discovered is that most galaxies experience red shifts instead of blue shifts, okay? Red shift meant that most galaxies are receding from us. Instead of approaching us, they're moving away from us. So this became known as the cosmological red shift. So the fact that most galaxies were moving away from us was an indication that space itself must be expanding. Not just the fact that galaxies are moving, space itself is expanding, and it's causing galaxies to move away from us more than come towards us, you see. So this became known as the cosmological redshift. It is related to, but slightly different in meaning than the Doppler shift. Doppler shift will happen anytime a galaxy is coming towards you or moving away from you, whether or not space is itself expanding, you see. But if space is expanding, it will cause more galaxies to move away from you than galaxies moving toward you, you see. If space wasn't expanding, it would be about even. Half the galaxies would move away, half the galaxies would move toward you, you see. But since space is expanding, most of the galaxies are moving away. The Doppler shift is the shifting of the spectral lines of galaxies due to the actual motion of galaxies. The cosmological redshift is due to the fact that the space between galaxies is expanding. You see that? So it's a slightly different in nuance. The space is expanding. So, of course, eventually this became known as the Big Bang Theory, okay? I believe the person who nicknamed that the Big Bang Theory did it because he actually didn't believe in the Big Bang Theory. It was Fred Hoyle. So he did it to kind of mock this theory, the Big Bang Theory. He believed in the steady state model of the universe. There were competing models of the universe, the static model, steady state model, and then the Big Bang Theory. So it was actually coined as a joke against it, but then the term stuck, and now we believe in the Big Bang Theory. So this can be explained by the raisin pudding or the button balloon model of the universe. Well, what do we mean by that? Let's put up this picture. You see here? So if you take a balloon, and this is what we mean by the button balloon model, just take a regular balloon and just attach a bunch of buttons to it, and now start blowing air into the balloon, you see? And now the balloon is going to expand. And even if the buttons are standing on it, it's fixed, they're not moving, but it's going to appear that they're moving away from each other, you see? So this is the space expanding effect. But on top of that, I can start making the buttons slide along the balloon if they're sliding. Then it might, if this one is sliding, they might appear as if they're approaching each other, or they might appear as if they're moving away, you see? So that's kind of what's happening. Some galaxies are sliding along that balloon, and they're actually approaching each other. But for the majority, since the space is expanding, most galaxies are moving away from each other, you see? And that's what's happening. So the reason this led to the Big Bang model is because if you take this movie and run it backwards, so visualize the universe as a movie, the movie is running forward, right? And now run it backwards, and then go back in time, and then you just conjure up the fact that one day the universe must have been very, very small, you see, running the movie backwards. So this model led to the Big Bang. And as far as the raisin pudding, same concept. If we come over here, same idea. If you take a cake, you're baking a cake, and you take some raisins in the cake and you put it, and now you take that cake and put it in the oven, and then the cake is naturally going to grow, right? You see that? So what's going to happen to the distance between those raisins? If two raisins were like 1 inch apart, and let's say these two raisins were 2 inches apart, these two raisins were 3 inches apart, right? 3 inches, let's say 1 inch and 2 inches. Okay, if the cake doubles in size, what's going to happen? So that's equivalent to saying the universe doubled in size. Then these two raisins, which were originally 1 inch apart, are going to be 2 inches apart. This one was 2 inches, and it's going to double. It's going to be 4 inches apart. And then these two raisins, 6 inches apart. You see? So notice all the distances doubled. So the farther away the raisins were to begin with, because the distance is doubling, they're now even farther away, you see? They experienced a change of distance from 6 to 3. That's 3 inches, you see? Now, these ones were closer to start with, and then they doubled. They only went from 1 to 2. So they only had a change of distance of 1 inch. And then this one went from 2 to 4. They had a change of 2 inches. So we could actually come up with the Hubble relationship. The velocity is equal to the Hubble constant times the distance. The distance is the original distance that they are. The Hubble constant tells you at what rate the universe is expanding, and then the velocity tells you how fast the raisins are moving away from each other. You see? How fast the raisins are moving away. So you can see that if you get 1 inch, then whatever the Hubble constant is, the velocity is going to be a certain number. If the original distance was 2 inches, it's going to be twice the velocity. And if the original distance was 3 inches, it's going to be 3 times the velocity. So these raisins are moving away from each other 3 times faster than these raisins. And then these raisins are moving away from each other 2 times faster than this one. You see? Just using a simple analogy of raisins in a cake, you can kind of understand what the Hubble law is. This became known as the Hubble law. Okay? V equals hd, very, very important law. And it kind of makes sense. The closer two raisins are to begin with, the slower they move away from each other. If they're 2 inches, they move each other twice as fast. 3 inches, 3 times as fast. Okay? Then the key question is, what's the Hubble constant? Okay? It took many, many years for people to agree on the constant. A lot of arguments went back and forth. Okay? Because the measurement techniques in the 1930s, 1940s, 1950s, they weren't that strong. They weren't that good, you know. So we'll come back to the Hubble constant when we're on this side of the page. So Hubble essentially proved that the universe is expanding, okay, by proving that equation. See, so basically the structure of the universe, and then the universe is expanding. But you cannot say, when you look at a picture like this, it looks like there is a center to the universe. And then we ask, where's the center? You can't really say that there is a center, because no matter what galaxy you're in, no matter where you live, it's still going to appear as if the other galaxies are moving away from you. So there is no such thing as a center to the universe, because even if you did live here, you're moving away, and you're moving away, and you're moving away. So there really is no way of defining what the center of the universe is and what the edge of the universe is. So all other galaxies are moving away from each other